Okay, in the previous lecture we were discussing inverse Laplace transform using partial fractions. And in this lecture, I'll solve one type of example which was remaining in the previous lecture. So find the inverse Laplace transform of 3s plus 5 upon 4s square plus 12s plus 9. We have done this or not? Please check.
Yes, sir, we have done this.
Yes, sir, we
Yeah,
have
done
done
this,
this.
sir.
Okay,
Yes.
okay, no problem then. So we have completed this. So this one 3s plus 1 upon s minus 1 s square plus 1. This,
Sir, this is also is completed.
okay. So we have completed all the tags. Fine then. So we will move ahead towards the next point, that is application of Laplace to the differential equation. Application to the differential equation. So the overall idea is uh, we will have a differential equation, say an or simply phi of d acting on y is equal to f of x. This kind of differential equation we will have. So what I'm going to do is I'll take Laplace transform. Phi of d on y is equal to Laplace of f of x. Okay, and I will solve it. When we solve it, when you solve the differential equation, in the linear differential equation, we have seen that we find this value of y. Okay, so in the same thing we are going to do. We are going to solve it, means that I need to find the value of y. So when I take the Laplace transform, I'll get a term capital Y of s. What is capital Y of s? It is nothing but Laplace of y. Okay, when you take Laplace of y, you will get capital Y of s, and you will get something P of s upon Q of s. This type of thing you will get when you take the Laplace transform and simplify. Now, what I need to find is y. Capital Y of s is nothing but the Laplace transform of it. So now what I will do is I will apply inverse Laplace. Right? Inverse Laplace. When I take the inverse Laplace transform of this capital Y of s, what we get is small y of t or x. On the other side, Laplace inverse of cap p of s upon q of s. So when I want to find inverse Laplace of p of s upon q of s, we use the partial fraction or some other method, and we solve the right hand side, and that will be the solution. So differential equation will be given. You take the Laplace you find the value of capital Y of S. Once you get capital Y of S, then you take inverse Laplace transform of both the sides, and we will get the solution of the given differential equation. So this is the complete method. Okay. So as we have this complete method, I will just recall how you take the Laplace transform of the derivative, as many of the students were absent that time, and then we will go to finding the solution of differential equation. So recall. 1. Laplace transform of y dash. So what we saw was Laplace transform of f dash of t. So the formula was s times Laplace of f of t minus f of 0. So this Laplace of f of t we wrote as capital F of s minus f of 0. So here what we will have is s times Laplace of y of t or y of x minus y of 0. So s times capital Y of s minus y of 0. This is the Laplace of y dash. So in the same manner, I can find the Laplace of y double dash as s times Laplace of y dash minus y dash at 0. Now s in bracket Laplace of y dash is s times Laplace of y minus y of 0, bracket complete, minus y dash at 0. So this is s square capital Y of s minus s times y of 0 minus y dash at 0. And the third one, Laplace of y triple dash. Now you can generalize from this what we will have: s cube capital Y of s minus s square y of 0 minus s y dash at 0 minus y double dash at 0. If you want, you take a screenshot of it. While solving examples, we will use this directly. And if you are not able to remember this, what you do is you understand just the first formula, because all of the below are derived from this one. You use this again and again, you will get the required result. So now let's solve the examples. Example 1. Find the solution of y double dash minus 3 times y dash plus 2 times y is equal to 12 e to the power minus 2t. So y of 0 is equal to 2, y dash of 0 is equal to 6. So taking Laplace on both the sides, taking Laplace on both sides, what do we get is the Laplace of y double dash minus 3 times Laplace of y dash plus 2 times Laplace of y is equal to 12 Laplace of e to the power minus 2t. So we have the formula for Laplace of y double dash, s square capital Y of s minus s times y of 0 minus y dash of 0 minus 3 times Laplace of y dash is s times capital Y of s minus y of 0 plus 2 times capital Y of s is equal to 12. Laplace of e to the power minus 2t is 1 upon s plus 2. Now we have the value of y of 0, y dash of 0 given in the question itself. So we'll use it. And for the first one, what I will do is I'll take y of s common from whole of the equation. So y of s is here, here and here. Collect the coefficients, s square minus 3s plus 2 capital Y of s. Y of 0 is 2. So minus 2s plus 6. Then y dash of 0 is 6. So minus 6 is equal to 12 upon s plus 2. This 2 will get cancelled out. So what we have, s square minus 3s plus 2 capital Y of s is equal to 12 upon s plus 2 plus 2s. So we can cross multiply and simplify this. So that will be 12 plus 2s in bracket s plus 2 upon s plus 2 into s square minus 3s plus 2. So which can be further simplified as 2s square plus 4s plus 12 upon s plus 2 s minus 2. The last one will be s minus 1. Is everyone clear up to this? Now, you have capital Y of s. What I need to find is small y. And how can I get small y? By taking inverse Laplace. So what we will do now is taking inverse Laplace transform. So I'll rub this part. Now taking inverse Laplace on both sides. What do we have? Laplace inverse of capital Y of s is equal to Laplace inverse of 2s square plus 4s plus 12 divided by s plus 2 s minus 2 and s minus 1. Now what is the left hand side? Left hand side will be simply y of t. What about the right hand side? How can we solve the right hand side? Anyone? Anyone? How to solve the right hand side?
Separate it.
Using,
Partial fraction.
yes.
Partial fraction.
So using partial fraction, using partial fraction, what we have to do is we have to write down this 2s square plus 4s plus 12 upon s plus 2, s minus 2, s minus 1 as a upon s minus 1 plus b upon s minus 2 plus c upon s plus 2. So by partial fraction we can do this. Now do the cross multiplication. So we'll have 2s square plus 4s plus 12 is equal to a into s minus 2 s plus 2 plus b into s minus 1 s plus 2 plus c into s minus 1 s minus 2. Now you have to put the values of s so that two of the things will be 0, either a or b. So if I put s is equal to 1, then look, b will become 0, c will become 0. So what we will have, 2 plus 4 which is 6 plus 18 is equal to 1 minus 2 which is minus 1 and 3 minus 3a. So which gives me a is equal to minus 6. Please understand why I am putting s is equal to 1. Then I will put, I need a and c to be 0. Look at the common term, s is equal to 2. Then we will get the required answer. So if I put s is equal to 2, then a and c will become 0. And from the second one, what do we have? So 2 square, 4, 4 to 8, 8 plus 8, 16. So this gives me b is equal to 7. And the last one, you put s is equal to minus 2. Then we put s is equal to minus 2. Then we will get c is equal to 1. Okay. So we have separated it successfully. Sorry for the problem. There was some technical problem going on. So we can put the values and we can find the inverse Laplace transform. So Laplace inverse of capital Y of S is equal to Laplace inverse of, let's separate this, minus 6 upon S minus 1 plus 7 upon S minus 2 plus 1 upon S plus 2. So Laplace inverse of capital Y of S is small y of t. So y of t is equal to minus 6 Laplace inverse of 1 upon S minus 1 plus 7 Laplace inverse of 1 upon S minus 2 plus Laplace inverse of 1 upon S plus 2. So y of t is equal to minus 6 e to the power t plus 7 e to the power 2t plus e to the power minus 2t. This is our final solution. Anyone having problem? Take 2 minutes, read it carefully, understand it, and you have any problem, then you can ask. Okay. Next example, solve y double dash plus y is equal to t, where y of 0 is equal to 1 and y dash of 0 is equal to minus 2. So what we have to do, taking Laplace on both the sides. Taking Laplace on both sides. So Laplace of y double dash plus Laplace of y is equal to Laplace of t. So Laplace of y double dash, we have a formula s square capital Y of s minus s y of 0 minus y dash at 0. plus capital Y of S is equal to Laplace of t is gamma of 2 upon S raised to 2. Let's collect the coefficient of capital Y of S. We'll have S square plus 1 capital Y of S minus Y of 0 is 1, so minus S. Y dash of 0 is 2 minus 2 is equal to gamma of 2 is 1 upon S square. So let's simplify this. S square plus 1 capital Y of S is equal to 1 upon S square plus S plus 2. I've done some mistake or what? Y dash of 0 is minus 2. Y dash of 0 is minus 2. So this will become plus 2. So capital Y of S is equal to 1 upon S square in bracket S square plus 1 plus S minus 2 upon S square plus 1. So I have two questions now. Can you take Laplace inverse of 1 upon S square plus 1, and Laplace inverse of S minus 2 upon S square plus 1?
Sir, we can take off s minus 2 upon s square plus 1 directly.
Who's it speaking? Yes or
Yes.
yes? How can we take it directly?
Sir, just separate the numerator and
Yes, very good. What about the first one?
Sir, integration
No,
0 to t.
sir, whole square.
no. Okay, so first can also be solved directly by let's see how. So in this case, you don't need partial fraction. So partial fraction is useful when your denominator can be factorized and it is having less power and you cannot solve it by some other way. So in that case, you go for partial fraction. But in this case, you can take the inverse Laplace easily. Taking inverse Laplace. So Laplace inverse of capital Y of S is equal to Laplace inverse of 1 upon S square plus 1 plus Laplace inverse of S minus 2 upon S square plus 1. So what I will do is I will add S square in the first one as well as I will subtract S square. After doing this, I will separate. So Laplace inverse of capital Y of S, small y of t is equal to. So now I will separate the denominator. What do I have? 1 plus S square upon S square into S square plus 1. Then you have minus S square upon S square into S square plus 1. So I have adjusted the denominator in the numerator. And for the second one, I will have Laplace inverse of s upon s square plus 1 minus Laplace inverse of 2 upon s square plus 1. Now here s square plus 1 will get cancelled out, and in the second one s square will get cancelled out. So y of t is equal to Laplace inverse of 1 upon s square minus Laplace inverse of 1 upon s square plus 1 plus Laplace inverse of s upon s square plus 1 minus 2 times Laplace inverse of 1 upon s square plus 1. So y of t is equal to Laplace inverse of 1 upon s square t raised to 2 minus 1 upon gamma of 2 minus 1 upon s square plus 1, that will be sine of t. Even the last one is sine of t, minus 3 sine of t. And in this one, plus cos of t. So this is the final answer. So not necessarily in every example we will have to find this using partial fraction. Some can be solved even without the partial fraction. Next example. Solve dy by dt plus 3 times y of t plus 2 times integral 0 to t y of u du is equal to t, given y of 0 is equal to 0. Look, this is not a differential equation now. This is integro differential equation because there is an integration as well as differential. Still, we will apply the same method, taking Laplace on both the sides. Taking Laplace on both sides. So Laplace of dy by dt plus 3 times Laplace of y of t plus 2 times Laplace of integral 0 to t y of u d is equal to Laplace of t. Now Laplace of dy by dt is s into capital Y of s minus y of 0 plus 3 times capital Y of s plus 2 times Laplace of integration with the formula 1 upon s into Laplace of y, which is capital Y of s. Laplace of t is gamma of 2 upon s raised to 2. Y of 0 is 0, so this term will vanish. Collect the coefficients of capital Y of s plus 3 plus 2 by s capital Y of s. On the other side, 1 upon s square, so which gives me capital Y of s is equal to so if you cross multiply, you'll get s square negative s square plus 3s plus 2. So 1s will get cancelled out. So y of s is equal to 1 upon s. Can factorize the middle term in the second one. What we have is s plus 1, s plus 2. So by partial fraction, what we will do is we'll write down 1 upon s, s plus 1, s plus 2 as a upon s plus b upon s plus 1 plus c upon s plus 2. So we will do the cross multiplication, and what we have is 1 is equal to a into s plus 1, s plus 2 plus b into s plus 2 into s plus c into s plus 1. So put s is equal to 0. Then we'll get a is equal to 1 by 2. Then we will put s is equal to minus 1. Minus 1 plus 2. So b we will get as minus 1. Then we will put s is equal to, I need minus 2. Then you will get the value of c, which is plus 1 by 2. Put the values over here. So I will write taking inverse Laplace transform. Taking inverse Laplace of 1. So we'll have y of t is equal to Laplace inverse of 1 upon s, s plus 1, s plus 2. By partial fraction, we have got this as Laplace inverse of a is 1 by 2. So 1 by 2 upon s minus 1 upon s plus 1 plus 1 by 2 upon s plus 2. Laplace inverse separates over addition and subtraction. So Laplace 1 by 2 Laplace inverse of 1 by s minus Laplace inverse of 1 upon s plus 1 plus 1 by 2 Laplace inverse of 1 upon s plus 2. So now it is, just the formula which is to be used for each and every one of them. So this is 1 by 2 Laplace inverse of 1 upon s is 1 minus Laplace inverse of 1 upon s plus 1 is e to the power minus t plus 1 by 2 e to the power minus 2. This is the final answer and the solution of given integral differential equation. Okay, that's it about solving inverse Laplace transform. Sorry, solving differential equation using Laplace transform. If you have any difficulties, you can ask. No problems. Okay, fine then. We'll stop here. In tomorrow's lecture, we will have the tutorial on the Laplace 10:45 to 11:45. Okay.
Excuse me, sir.
Okay, sir.
Yes.
Hello.
Yes.